Hello everyone, my name is Jay Lim and I'm a PhD student in Rutgers University with my advisor Santosh Nagarakate. Today I want to present a radical approach in developing math libraries for new number representations that are being proposed recently. Everyone is designing new representations for approximating real numbers. These representations are proposed to provide high throughput as well as sufficient amount of accuracy. All of these representations are used in numerical applications, so they need math libraries. So in this presentation, I would like to propose a really cool novel approach to create fast and correct math libraries. The key insight in our approach is to approximate the correctly rounded result of elementary function f of x and reduce the problem of generating polynomial approximations to a linear programming problem. Using our approach, we created RLibM, a math library generator, and a collection of fast and correct math libraries for various representations. Now, before I introduce our new exciting approach, let me first describe what a correct math library is using this real number line. As you know, fixed precision representations like floating point representations can only represent finite number of rational values. So you can't exactly represent irrational values like natural log of x1 with these representations, and you have to round these kinds of values to a representable value. In our example, I am using the round to the nearest tie goes to even rounding mode, which is the most common rounding mode. So natural log of x1 rounds to the value v1. So if our natural log of x function produces v1 for the input x1, then we say that it produces the correctly rounded result for the input x1. If our natural log of x function produces correctly rounded result for all inputs, then we say that it is a correctly rounded function. Finally, if all approximation functions in a math library are correctly rounded functions, then we say that the math library is a correctly rounded math library, or correct math library for short. In the past, prior approaches have focused on approximating the real value of an elementary function f of x using polynomial approximations. However, this caused a set of problems in generating the correctly rounded result, because even the tiniest amount of error in the approximation will round to an incorrect result. But really, we should not be approximating f of x. Yes, it is true that the point of math libraries is to approximate f of x, but that's not what the result of the math libraries are. The result of the correct math libraries is the correctly rounded result. So we should really be approximating the correctly rounded result. This allows us much larger freedom in generating efficient polynomial approximations because we can produce any values in this gray region, whether it be this value, or this value, our computed result will round to the correctly rounded result. Okay, great. So now how do we generate a polynomial that approximates the correctly rounded result? Well, first, we use an oracle that can accurately compute our elementary function f of x and compute what the correctly rounded result should be for each input. For each correctly rounded result, we identify an interval of values where all values in the interval round to the correctly rounded result. We call this interval a rounding interval. In essence, the rounding interval defines the lower bound and the upper bound of the polynomial that we must generate for each input. In fact, they define linear constraints for solving for the coefficients of the polynomial. So we can encode these linear constraints into a system of linear inequalities and use linear programming solver to generate a polynomial that satisfies all the constraints. Using this approach, we created RLibM, a collection of math libraries for bfloat16, posit16, and 32-bit float representations. By approximating the correctly rounded result of f of x, we were able to create fast math libraries that produce correct result for all inputs for all of our functions. In conclusion, it is a great time to design new number representations, and they all need math libraries. So we propose a radical approach to design math libraries. Our key insight is to approximate the correctly rounded result of f of x instead of the real value of f of x. Additionally, we frame the problem of generating polynomial approximations as a linear programming problem. Using this approach, we generated RLibM, which is fast and correct. Please try RLibM and our math library generator, which are both available online. Thank you very much.